Hello, everyone. Welcome to today's reading group. Our topic for today is oversmoothing of graph neural networks and its solutions. So the contents for today consists of two parts. The first part is what is the oversmoothing problem. In this part, I will give a brief introduction and I will introduce when does the oversmoothing problem happen, and I will give a theoretical analysis. This part's main focus are the following two papers. One is the graph neural networks exponentially lose expressive power of no classification. This is a paper published in iClear 2020. The second paper for this part would be tackling oversmoothing for general graph convolutional networks, which is published in TPAMI journal this year. And the second part for today's topic would be the solutions of the oversmoothing problem. So in terms of the solutions for oversmoothing, there are basically two different types of methods. The first method is to modify the network architecture. An example of this type would be the paper published in this year's ICML, which is simple and deep graph convolutional networks. The second type of solution would be modify the graph structure. An example would be DROPEDGE towards deep graph convolutional networks on node classification, which is published in iClear 2020. This DROPEDGE actually also has the journal version, which is tackling oversmoothing for general graph convolutional networks, which is actually this paper. In my presentation, I will not introduce these 1, 2, 3, 4 papers one by one, but I will mix their contents together. But basically, I will follow the order of this content. Okay. So now let's start the first part. What is the oversmoothing? So the oversmoothing problem is saying that when the network is very deep, then signals of neighboring nodes get mixed together and go indistinguishable by applying the Laplacian type graph convolutions. So this oversmoothing is one of the key reasons that impedes the graph neural networks to go deeper. So here is an example to show the oversmoothing problem. So in this example, we are using a Zatori Rice Club network, which includes 34 nodes, 78 edges, and 2 classes. And the figure A, B, C, D, E corresponds to the output embedding of GCNs with 1, 2, 3, 4, 5 layers. And then we can see that when the GCN is very, very shallow, such as 1 layer and 2 layer, then these nodes are becoming distinguishable. But when we further increase the number of layers of this graph convolution network, let's say we use 3, 4, 5 layers, and then we can see that all these nodes are becoming less distinguishable when the network goes deeper. So here's another example for the oversmoothing phenomenon. So this time, instead of showing the embeddings, the distribution of the node embeddings, we check the loss curve during the training and validation. So this example is on the Cora dataset and is on the node classification task. And then we can see that the green curve corresponds to the 8-layer GCN, while the blue curve corresponds to a 2-layer GCN. And then we can see that with the 2-layer GCN, the training curve converges very well. But when we increase the number of layers to be 8, then we can see that for this deeper GCN, the loss does not converge. So it does not go down, which means actually this oversmoothing problem can impede the graph neural network to go deep. And here's the last example. And this example is on a sampled Cora dataset. So this dataset is constructed by sampling two connected components from the training graph of Cora, and then each component has a node number 640 and 54 and 26 respectively, and then this figure shows the distribution of the node embeddings, and then we can see this is the this is a distribution for the row feature, and this is after apply a 10 layer GCN. This is after applying a 100 layer GCN, and this is after applying a 400 GCN. And then we can see that when we increase the number of layers, then the nodes are becoming less distinguishable. So by the way, for these figures, a larger node means a node with a higher degree. Okay, so the conclusion for this example would be when the number of layers becomes larger, then the obtained embeddings will converge to a subspace like this. Okay, and then let's think about when does the oversmoothing happen? And here are actually three types of oversmoothing. So they are the oversmoothing phenomenon for different GCN variants. So for the first figure, this figure A is a GCN with a linear activation. And then we can see that this GCN with a linear activation will converge to a certain point like this. And this figure B would be GCN with ReLU activation, which is actually a nonlinear activation. And we can see that then GCN with this ReLU activation will converge to a certain subspace. And the subfigure C would be GCN with ReLU activation and bias. So a GCN is usually, a GCN model is usually implemented in this way with both ReLU activation and with bias. And then we can see for this type, the GCN will converge to a certain cubic. Now let's try to better understanding this oversmoothing phenomenon by seeing some of the theoretical analysis. So the first important theory we should know is the augmented spectral property. So here we are using this D hat to denote the degree matrix with the self loop, and then we are using this A hat to denote this normalized matrix. So the augmented spectral property is saying that given this A hat matrix, which is symmetric, and then let's lambda 1 until lambda n be the real eigenvalues of this A hat, sorted in an ascending order. And then let's suppose the multiplicity of the largest eigenvalue lambda n is m, which means we have lambda n minus m less than lambda n minus m plus 1 equals until equals lambda n. And then we have the following three propositions. First is the lambda 1 and lambda n minus 1 should be larger than -1 and smaller than 1. And the second one would be the lambda minus m plus 1 would be equivalent to and be equivalent to lambda n equals 1. And finally, we will have let this m be the number of connected components in the graph G, and we construct the eigenvector em in this way, where this should be the indicator of the m's connected components, which means UMI will be equivalent to 1 if this node I belongs to the M's components. Otherwise, UMI will be equivalent to 0. Then we know that this EM, with this kind of definition, we know that this EM would be the eigenvector associated with the eigenvalue lambda minus big M plus small m. So we are not gonna prove this theorem here, but the EM vector in this theorem is going to be very important. And at some later stage of today's reading group, we're going to show that an infinity deep GCN must converge to a linear combination of this EM. And then let's see some important definition before we come to the final theorem. So first is the definition of the subspace. We define a subspace M as matrix E times matrix C, where this C belongs to, where this C has a dimension big M times big C. And this C should be a m-dimensional subspace in the in this space, and this E will be equivalent to E1 until EM, which collects the basis of the largest eigenvalues of this A hat in this theorem. So essentially, E1 until EM vector are defined in this way. Here are some comments for this definition of subspace. First, this EC can be, this EC is actually a linear transformation of this E. And then also with this definition, we can find that for any node U and V, if we have node U and V have the same degree, which is du is equivalent to dv. And if U and V are in the same components, then we definitely know that EC's uth row will be equivalent to EC's vth row. So here's a simple explanation for why we have this kind of conclusion. So we just explicitly write down the formulas for the ith components in this ECU, and then we can see that these two would be equivalent because each E1U would be equivalent to E1V, and E2U would be equivalent to E2V until EMU is equivalent to EMV. This is because we would definitely have EJU equivalent to EJV when UV have the same degree and is in the same components. So with this definition of subspace, and then we define the distance with this subspace. So a distance between a matrix H and subspace M would be defined as dmH is equivalent to inf y minus h, take the Frobenius norm, where this y belongs to subspace M. So then with this distance, with subspace M's definition, we can define a cuboid. So a cuboid, which denote as this OMR, is a cuboid that expands this subspace M up to a radius R, where this R should be positive. So we can formally write it down as the OMR is equivalent to all the matrix H that that has a distance with the subspace M less than or equivalent to R. So this is a definition of a cuboid. And then now we have the definition of the subspace, we have the definition of the distance with subspace, and then we have the definition of this cuboid. Then we can first see a case study to show the conclusion that GCN with ReLU activation converges to the subspace M step by step. So this conclusion is actually introduced over here. So we are trying to prove this case B, GCN with ReLU activation. So first of all, we can prove the convergence. We can analyze the convergence of this actually A hat. This should be, and then we know that this should be A tilde, and A tilde should be the adjacency matrix with the self loop. So we can see that the distance between subspace M with this matrix should be less than or equivalent to lambda m plus 1 times this distance between subspace M and the matrix X, where this lambda m plus 1 should be some value less than 1, and it should be the second largest eigenvalue of A hat. So this lambda m plus 1 is, which is the second largest eigenvalue of A hat, which means it cannot, it does not belong to the it does not belong to the lambdas in this set. Okay, and then after we have the convergence of this A tilde, then let's see the convergence of this W. We know that the distance between subspace M together with matrix XWL should be less than or equivalent to SL times the distance between subspace M and the matrix X, where SL should be less than or equivalent to 1. And this is the maximum singular value of this WL. And then after we have the convergence of this W, we know we can have the convergence of the ReLU activation, where we have the distance between subspace M with the matrix after using this ReLU activation for a matrix S. X should always be less than or equivalent to the distance between subspace M together with the matrix X. So therefore, with this convergence of A tilde, convergence with W, convergence with ReLU, and we finally have the convergence of one GCN layer. So let's this HL plus 1 be the representation obtained from L plus 1 layer GCN. Then we have this DM, the distance between the embeddings of L plus 1 layer GCN and this subspace M should be bounded by lambda m plus 1 times SL times the distance between the subspace M together with the embeddings outputted by the else layer GCN. So since this lambda and S is less than 1, so lambda m plus 1 times SL is less than 1. So we know that this distance between subspace M and the GCN's outputted embeddings will get closer and closer, and we finally converge. So here's a more, so this is just a case study to show that the GCN with the ReLU activation will converge to the subspace M. And here's a more general conclusion, which is the universal oversmoothing theorem. So this theorem is not only applicable to this special case, but is also applicable to a lot of GCN's variants. So the theorem is saying that we would universally, for the GCN models and its variants, we would universally have this DM HL plus 1 minus R, it is less than or equivalent to V times this DM HL minus R. Well, this V should be larger or equivalent to 0, and R describe the convergence factor and radius. Okay. So V is the convergence factor and R is the radius. So here we should know that in this theorem, these GCN models defining equation 1 to equation 4 are the GCN with residual link, and GCN with bias, and some APPMP model. So these are just some variants of GCNs. We will mention these models later. And with this universal oversmoothing theorem, let's see how can this case study fit into this theorem. So if we compare this convergence formula with this theorem, we can see that actually for GCN with Briloup activation, we just simply set this R to be 0 and set this V to be lambda n plus 1 times SL. So here is how we can fit this case study into this more general conclusion. So these are all the theoretical results for the oversmoothing problem. Then after we have some understanding of what is this oversmoothing and when does it happen, and after we have some theoretical analysis, let's see how to solve this kind of oversmoothing problem. Okay. So the first type of methods to solve the oversmoothing problem is to modify the network architecture. So here are several types of works that can here are several works that are trying to modify the network architecture to improve its performance by adding the residual link. One is GNNs. That's a work in 2018. So this work tried to combine the representation of all layers by using an aggregator operator before the output. So which means, for example, if we have an L layer GCN, then we just get the aggregate the output of 1, 2, 3, 4, 5 until else layer, and then we use the aggregated embedding as our final output. So this aggregation operator can be either concatenation or maximum pooling or some other aggregator aggregators. And the second way to add the residual link is the REST GCN, which actually borrows the concept from the RESTnet, and it adds residual connections between the hidden layers. And the next way to add the residual link is instead of add residual connections between the hidden layers, it tried to add connection to the initial representation to the current layer. So as shown in the work of this 2020 paper, a connection to the initial representation will be more helpful than adding the connection between the two connected layers. And the last way to add a residual link is the GCNII, which is recent work and which is also the work I will introduce in detail in the following. So for this GCNII, except for the initial residual, we also add the identity mapping to the weight as well. So now let's, so actually, obviously the last one have the best performance. So I will only introduce the last work in detail. So now let's see the proposed method for this GCNII. The idea is very elegant. So basically we just add the initial residual and then we add the identity mapping in the weight. So here is a formal formula for a GCNII layer. So this is the nonlinear activation, which is quite common in the graph neural networks. And then we only need to focus things in these two brackets. So in the first bracket, we can see that we add an initial residual to the initial representation. And then for the second bracket, we can see that we add an identity mapping to these to the weight matrix. And then The identity mapping's main motivation includes the following. So first is that in this 2019 paper, it shows that a frequent interaction between different dimensions of the feature matrix may degrade the performance in the semi-supervised task. And then by applying this kind of identity mapping, we can reduce this interaction between different dimensions and therefore may help to improve the performance. And the second motivation is that in the work of 2017, so people find that a linear ResNet of this form, which is actually with the identity mapping in the weight matrix part. So this kind of linear ResNet satisfy very nice properties that includes the optimal weight matrices will have a smaller norms, and the only critical point would be the global minimum. So both of these two are very nice properties of this identity mapping, and that's the reason why the authors of this paper also try to add this identity mapping. And now let's see the importance of each of these two components. So first is initial residual enough? So in these figures, we only consider adding the initial residual, but we do not add any identity mapping. So we can see that with the initial residual, when the network goes deep on all of these three data sets, the performance drop is clearly alleviated. But it's still but the performance will still go down a little bit, which means it's not good enough. So only at this initial residual is not enough for us. So then we consider adding the initial residual together with identity mapping. So for now, we should check this red curve. The red curve is we have both initial residual and identity mapping, and the orange curve is we only have initial residual, and green curve is we only have the identity mapping, and the blue curve is we have nothing. And then we can see that for this red curve, it's when the number of layers increase, the performance does not drop and may even increase a little bit, which means the initial residual and identity mapping is actually very effective. So here's an overall results for these GCNII models on the semi-supervised node classification task. So according to the result, we can see that this GCNII and its variance, the variance is like this. So basically we just, in this variance, we just allow the initial representation and allow the propagated representation for the else layer to have different weight. Okay, so the only difference will be for here we allow these two parts to have different W parameters. So we can see that according to this table 2, we can see on all of these three data sets, the GCNII and its variants are having the best performance, and we can see it's much deeper than the other baseline models. So if we don't have this bracket, then that means we're using a 2-layer model. And this table 3 is a more complete result. So we just list all the models, including baseline models, GCNII and its variants, and then we record the results for 2, 4, 8, 16, 32, 64 layers, and then we can see that with the GCNII and its variance models, when the number of layers increase, when we go very deep, then we do not have this kind of huge performance drop, which means we successfully alleviate the oversmoothing problem. So this is for semi-supervised node classification. And we also have results for the supervised node classification. Again, we can see that the GCNII and GCNII's variance model consistently obtain very competitive results and with a very deep model. So this is for the GCNII, and then the other type of method would be according to our content. The other type of method would be modify the graph structure, where we have this drop edge method. So the drop edge method is actually very simple. So we just at every training epoch, we drops out a certain rate of edges of the input graph by random. So here's how we drop the edges. So just at each training epoch, we uniformly samples each edge in the adjacency matrix A with the probability I minus this P, which is A prime ij is equivalent to Aij times the Bernoulli distribution of 1 minus P. So then so this is the proposed method of this drop edge paper. The idea is very simple. And now let's try to compare this proposed drop edge method with several other related concepts. The first concept would be the drop edge with the dropout. So the dropout is actually trying to perturb the embedding matrix by randomly setting embeddings to be zeros. So this dropout is trying to perturb the embedding matrix, but for this drop edge, it tried to perturb the adjacency matrix. To compare the functions, the dropout only alleviates the overfitting, but it cannot help with the oversmoothing problem. But for the drop edge, it can alleviate the both problem. And also the dropout and drop edge are actually complementary to each other, which means we can use both drop edge and dropouts. The other concept we should compare the drop edge to would be drop node. So drop node is actually the node sampling based method. So so the difference between these two things are the drop edge is edge oriented, while the drop node is node oriented. So for the drop edge method, it would be possible to preserve all nodes features for the training. So if they can be fitted into the memory at once, which means it may exhibit more flexibility. And the last concept we should compare the drop edge with is the graph spacification. So graph spacification is actually a very classic research topic. And a lot of people has already done some related research to this field, but this is quite different with the drop edge. So for the graph spacification, its goal is to remove some unnecessary edges for the graph compressing purpose, and we want to keep almost all information of the input graph. But for drop edge, we do not have this kind of optimization objective. And also for the graph spacification, once the edges are discarded, then the output graph will keep unchanged. But for the drop edge, we would modify the graph structure at the beginning of every epoch. So, for example, at one epoch, some edges are discarded, and then at the next epoch, we may still have this edge exist. Okay. So after compare the drop edge to some of our familiar concepts, and now let's see the theoretical analysis for this drop edge. So here's a theorem for the drop edge. we denote the original graph as G and the one after dropping certain edges out as G prime. Then regarding the GCN models in equation 1 to equation 4, which are the four GCN variants we introduced before. And then we assume by V and M the convergence factor and the subspace on G and V prime M prime on G prime. Then we have either of the following inequalities holds after sufficient edges removed. So first is the convergence factor and the radius only increases, which means we definitely have V would be less than or equal to V prime. And we also have the information loss is decreased, which means n minus dime m will be larger than n minus dime m prime. So for the first point here, we should note that the convergence factor increases means it will converge slower, which also means that we can slow down the degeneration speed. And for the second point, we should notice that the gap between dimensions of the original space and the convergence subspace, which is a minus m, actually measures the amount of information loss. So a larger gap would mean a more severe information loss. And according to this second point of this theorem, we know that this drop edge is able to increase the dimension of the convergent subspace, and therefore we know that it is capable of reducing the information loss caused by the dimension collapse. So here are a visualization results for how this drop edge can help us alleviate the oversmoothing problem. So the above figure is for GCN and the lower figure is for GCN with the drop edge. So in the above figure, we can see that the nodes are generally distinguishable at the very beginning. And then when we increase this D, which is the depth, the number of layers for the network, and then we can see that the distance with the subspace M, so we can see that this is dm, will decrease dramatically. And it finally achieves a very small value when we have 400 layers. And then it is clearly shown that when this D is equivalent to 400, which means after applying a very deep GCN, then the nodes with different components would have a collinear on two different lines. So this is on this line and this is on this line. So which means the bigger the node is, the farther it is from the 0 points. And this kind of observation would be consistent with our previous theorems. And in the lower figure, which is GCN with the drop edge, so we can find that first the convergence to the subspace become much smaller. So we can see this dm decrease much slower. And we can also see that the number of connected component is larger when we perform this drop edge on GCN with the dropping rate p equals 0.5. And if we decrease it, if we increase it to 0.7, then we can find that the convergence speed will be further decreased. So these two figures, if we compare these two figures, we can find this drop edge is very helpful for the for alleviating the oversmoothing problem. And these results is to show that this drop edge method can be combined with not only the GCN but also its variants. So so we can see that this is GCN with and without the drop edge. So if we consider if we compare this blue curve and the orange curve, we can see that the orange curve has a better performance, which means and with the number of layers increase, and then let's say increase to 64, this orange one have a much better performance, which means the drop edge do have some very important influence on the performance. And this is drop edge compared with GCN with bias. And then again, we can find that the orange curve would be somehow helpful if somehow better than this blue curve, which means the drop edge also helps with the GCN with a bias. And this one is REST GCN, which is to add the residual link between every two connected components or every two connected layers. And then again, we can find the orange curve is above the blue one, which means drop edge can also help with this case. And the last one is the JK nets, which is which is trying to alleviate the output of every layer, and we aggregate this output as our final output, and then we can see that with this JK nets, the drop edge again is very helpful. So here are some curves for the validation loss on different backbones with and without the drop edge. So we can see that we can find that the curves of both training and validation can actually we can find that the curves of this validation are become much better than after applying this drop edge. So this can also explain the benefit of this drop edge method. And then finally, we have this big table explaining some results for this drop edge. And we can have some findings with this table. First, we can see that the drop edge obtains a very significant enhancement against all the baselines. And particularly on the Cora and Sciseer dataset, the best accuracies obtained by the models of with the drop edge method is becoming much better than the previous best results. And also we can see that for most models with the drop edge, the best accuracy is obtained is obtained under a depth beyond 4, which means the drop edge would help to formulate a deeper network and alleviate the oversmoothing problem. And also for this table, the fast GCN, AS GCN, and GraphSage are can be considered as the drop node methods of GCNs. And we can see that the drop edge based approaches can outperform these drop node based variants, which somehow can also confirms the effectiveness of this drop edge. Okay. So that is all for this topic. So let's use this content to do a brief review of what we have been discussed for today. So first we discuss what is oversmoothing problem. So the oversmoothing problem is saying that when the network goes deep, the nodes are mixed together and becoming even more indistinguishable than using a shallow network. And for the oversmoothing problem, when consider when does it happen, so we have 3 different kind of understanding. So first is for the GCN with a linear activation, it will converge to a certain point, and for the GCN with a ReLU activation, it will converge to a subspace, and then with a GCN with ReLU activation and with the bias, it will converge to a cubic, and then we provide a Mann theorem, which is a universal oversmoothing theorem, which is to illustrate a general conclusion for the oversmoothing problem. And then we move to the second part, which is the solutions of the oversmoothing problem. So basically, the methods can be divided into two types. One is to modify the graph, the network architecture. So to modify the network architecture, we are trying to add the residual links, and we also trying to add the identity mapping in the weight section. And then the second type of solution would be modify the graph, which is to drop a certain number of edges at the start of every training epoch. And the experiments results shown both type of methods are very effective, and these two type of methods are actually comprehensive to each other. So that's everything for today's presentation. So please let me know if you have any questions. Thank you.